Nothing in this lecture is going to be anything you haven't seen before, I don't think. This is pretty much all review material. Just to remind you of polar coordinates, how to convert between our ordinary coordinates and whatnot. So let's start with how these things work out. So I'll start with, in the first quadrant, let's say I have a point that I want to call x comma y. Well, the way to change this to what is known as a polar coordinate system is to draw a line from the origin to the point. I always figured I could fix my point if my line didn't quite make it. And we let theta be an angle that starts at the positive x-axis and goes up to this line that connects x and y. And the distance from the origin we call r for radius. And if you drop a perpendicular straight down from the point, you create a triangle, a right triangle. The height of the right triangle is y. The base of the right triangle is x. And you know from trigonometry that cosine of theta equals adjacent over hypotenuse. So that equals x over r. Or if I multiply through by r, x is equal to r cosine of theta. Similarly, you'll get sine of theta equals y over r, and so y equals r sine of theta. Now those are good for the first quadrant. But what about other quadrants? For example, if I'm in the second quadrant and say my xy is somewhere in the second quadrant, and I'll draw the radius to the origin. There's xy, and theta measures the angle between the positive x-axis and this line. And there again is r. And notice we can do another triangle. You might remember they refer to these as reference triangles. You went to the nearest x-axis you could to create yourself a right triangle. And then here, notice it's a little bit different. The height of this thing, while it is y, the base of the thing, see, x is negative to the left of the y-axis. So this distance down here, if I'm going to use that for a distance, is actually the absolute value of x. And in this little crook, this little angle of the triangle, that angle is pi minus theta. So let me do the same things I did before. I'll start with cosine. Cosine of pi minus theta equals adjacent over hypotenuse. So that's the absolute value of x over r. All right, well, I can use the sum of angles formula for cosine to rewrite that side as cosine of theta, cosine of pi, cosine of theta plus sine of pi sine of theta. And the other side, since x is known to be a negative number, the absolute value of it is equal to negative x. R was no problem. It was still a distance between the point and the origin. Sine of pi is 0. Cosine of pi is negative 1. So I get negative cosine of theta equals negative x over r. When I simplify and multiply through by r, I get x equals r cosine of theta. And I don't have to make any changes to the formula. All I have to do is say x is r cosine of theta. And likewise, this is the y part's no different. Go through the same process and you'll see that y equals r sine of theta. And in fact, we might as well put a box around it because it doesn't matter what quadrant we're in. If theta was in the third quadrant, or if the point was in the third quadrant, the same kind of tricks will apply to show you that I get these exact same equations in the fourth quadrant. I don't need to say any more than that. So I can just say no matter what, x is equal to r cosine of theta, y is equal to r sine of theta, no matter what. It doesn't matter where that's located. And r, you may remember that r is the square root of x squared plus y squared, that you get directly from the Pythagorean theorem. And I guess the only thing to do is probably do a few examples, remind you of this kind of stuff, but we're not going to spend a lot of time. This is obviously supposed to be a review. So for example 1, let's convert, and I'll try to be specific which points are given and which ones you want to find. I want to convert xy to, goes by 4, 4 to polar coordinates. That means to find an r and a theta. So let's go ahead and do those things. The r is easy enough. R equals the square root of 4 squared plus 4 squared. That equals the square root of 32, which is 4 radical 2. And theta, well, that's a little more complicated. What I should do is come back to this triangle, maybe the first triangle I showed, especially since 4, 4 is in the first quadrant. It'll look most like this picture. I don't really talk about theta other than that x equals, that x and y equal something in terms of theta. I don't really discuss theta by itself. But one thing that works for all the quadrants also, if you remember, tangent of theta is opposite over hypotenuse. So up here where I had my other formulas, let me put the tangent of theta equals y over x. So let's come back down here. Maybe I should put it actually here again, in case you just want one page for all of the formulas at once. I suspect you have these memorized, but whatever. So that means I'm going to put tangent of theta, and my y and my x are both 4. So tangent of theta is equal to 1. So how do you get theta? Well, you probably know that the tangent of pi over 4 is 1. But another thing, you can even use your calculator for this. Theta is simply arctangent of 1, which equals pi over 4. So that's what we mean by converting to polar coordinates. Your r theta, if you will, r theta equals 4 radical 2. Put the r first, the theta comes second. That's pretty standard. That's why I labeled it as well, so you know which one's which. Both very simple calculations. The pi over 4 was pretty simple. You probably could have guessed pi over 4 just because x and y were the same. You knew that it had to be halfway between starting at the x-axis and ending at the y-axis. Let's convert x comma y equals 3, 4 to polar coordinates. So r equals the square root of 3 squared plus 4 squared equals 5. Tangent theta equals 4 over 3. So theta equals arctangent of 4/3. There's no need to simplify that or try to figure out what it is. It's not one of the angles that we know. So this is good enough. Make sure your calculator is in radians. I keep telling you. And the fact that I keep talking to students who are in degree mode means that people are not watching these videos. I don't, personally, I think they can help you fall asleep, but nonetheless. Convert x comma y equals negative square root of 3 comma 1 to polar. So same deal. R equals the square root, negative square root of 3. That quantity will be squared, plus 1 squared. That will equal 2. Tangent of theta equals 1 over negative square root of 3. And where does tangent equal 1 over negative square root of 3? Now, if you know, here's the way that I jog my memory. This is a little aside stuff, but here's what I think of. Tangent theta is supposed to be sine of theta divided by cosine of theta, right? And I know that when one of them has a radical 3, like when one's radical 3 over 2, the other one has a half. So if I look over here, I can see that the bottom has the radical 3. That means cosine of theta must have been radical 3 over 2. And then sine of theta would have been 1/2, or negative, or something like that. But the negative I'll take care of in a minute. Now, if that's the case, where is cosine equal to radical 3 over 2? Those are the pi over 6 locations, like pi over 6, 5 pi over 6, 7 pi over 6, etc. All those pi over 6s. So you can immediately tell me that theta equals some sort of a pi over 6. So I'm going to put pi over 6, and I'll figure out where in a minute. The easiest way to figure out where is to look at the point itself. Negative x, positive y. This point here is in quadrant 2. That means the cosine is negative and sine is positive. If that's the case, where is a pi over 6 there that would work? Well, it would have to be 5 pi over 6. 5 pi over 6 is in quadrant 2. That's the only one where cosine is one of the radical 3 over 2's. So there is your r and there is your theta. Now I want to warn you about something. I'll put a warning here. A little trick I did in the last example where I took the arctangent. If I tried to do that here and said theta is equal to arctangent of negative 1 over radical 3, and you put that in your calculator will give you the wrong answer. Watch what I mean. Your calculator is programmed, and indeed many arctangent functions are defined where it outputs an angle between negative pi over 2 and pi over 2. This angle here is not between negative pi over 2 and pi over 2. So if you took your calculator and tried to do arctangent of negative 1 over radical 3, even if you had it set to give you the exact answer and not some decimal version of it, it would give you negative pi over 6. If you were to convert that to 0 to 2 pi, you'd say that's 11 pi over 6. It's still wrong. The problem with it is negative pi over 6 is an angle that ends up in the 4th quadrant. You're in the 2nd quadrant. This will help you immensely on writing your answer. How do you get 5 pi over 6? Well, it is related to arctangent, but this is what you have to do. If I want that theta, if I want the actual theta from the problem, I have to add pi to my answer, so that while this thing here refers to something in the 4th quadrant, when you add pi, it takes you all the way back up to the 2nd quadrant. So you have to keep that in mind. If your angles are in quadrants 2 or 3, you're going to run into this issue. And you can bet that I am going to put something on an exam that has that happen. You are duly warned. Not just here, but verbally as well. Same deal. Here we're in quadrant 3, so keep that in mind when we're talking about the angle. R is easy. I'll have -2, that quantity will be squared, plus -2 radical 3, that quantity squared. Let me see, I have 4 plus 12, well that worked out nice, that equals 4. And then tangent of theta equals -2 radical 3 all over -2. In some ways it's almost desirable to leave it like this, but I'm going to simplify nonetheless. We end up with radical 3. So my mind is thinking this way. I'm thinking of it as radical 3 over 1 because that way the top or the sine portion of tangent is radical 3 over 2 and the cosine portion is 1/2. So where is sine equal to a radical 3 over 2? That would be at the pi over 3s, like pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. All those pi over 3s is where we'd get a radical 3. Which pi over 3 is it? Well, come and take a look at the quadrant we're in. The point itself is in quadrant 3. Well, what kind of a pi over 3 is in quadrant 3? 4 pi over 3. If you just tried to do arctangent, so if you just try to do arctangent of radical 3, your calculator would give you an answer of pi over 3. So you have to do the same game as before and add pi. One last example involving this conversion process. I think I've spent more time than I need to, but let's convert 4, 7, -4, -7. And I broke a promise already, and I should not have done that. Convert x, y equal -4, -7 to polar. Now you're in the fourth quadrant. R does not care what quadrant it is in. -4 squared plus -7 squared. No simplifying here, you just get the square root of 65. Tangent of theta equals -7 divided by -4. And here you can do the arctangent and get the correct answer because arctangent I surprised myself. Okay, anyways, here, the reason for this example, oh, now I understand why I did it. You still got to add pi to your answer. This here is in quadrant 3. So the answer here is, this is a quadrant 1 angle, so you have to add pi. But there's no, I don't know arctangent of 7/4. So I'm here to tell you that if you write your theta in that format, it's perfectly fine. Just like the square root of 65. We don't expect you to do anything else with it except write that. If we want an exact answer, this is what we're talking about. No decimal approximation of it. Let's go the other way. Let's convert r comma theta equals 4 comma pi over 3 to xy. That version of it is called Cartesian. So we'll say to Cartesian coordinates. Cartesian, of course, is after Rene Descartes, who invented these types of graphs. In fact, they call it a Cartesian coordinate system. I don't know why they don't call it a Descartesian, but whatever. Let's see. For this, if r theta is given, we wrote this earlier, x equals r cosine of theta. So that is 4 cosine of pi over 3. So x equals 4 times 1/2, which equals 2. Y equals 4 times sine of theta. So in this case, well, r times the sine of theta, which is equal to 4 sine pi over 3. That's 4 times radical 3 over 2. And so y equals 2 radical 3. And so there's our answer. X comma y equals, where was x? 2 comma 3. This time our theta equals 12 comma negative pi. Compute xy. Well, x equals 12 cosine of negative pi. That equals negative 12. Y equals 12 sine of negative pi, and that equals 0. So xy equals negative 12 comma 0. In your mind, that should make sense. If the angle is negative pi, that means we went clockwise until I got to the x-axis on the other side of the y-axis. So it makes sense that this point is there on the x-axis. We're going to spend a lot of time working with curves in polar coordinates. Polar curves, whatever you want to call them. And usually the way they're going to be written is something like r is going to be a function of theta. And to get us started, let me do an example. I think this is example 8. Graph r equals 3. Well, if you were to make a list of things, if I say r comma theta, this is no different than y equals f of x. So just like I make a y versus x chart, I can make an r versus theta chart. Well, if theta is equal to 0, what is r? 3. If theta is equal to pi over 6, what is r? 3. If theta is equal to pi over 4, what is r? 3. It doesn't even matter what theta is. I don't really care. It doesn't. You can put as many angles as you want over on the right hand side. R is always going to be 3. So what kind of a thing always has a radius of 3 no matter what angle? A circle of radius 3. Let's get your calculator to draw this. As you might have guessed, there is a polar mode. Click your mode button and go down to the 4th line, move over to POL and hit enter. And then when you hit your y equals, you will see things look a little bit different than ever before. R1, clear out what is there and replace it with 3. And you can do zoom 6 just like anything else, but let me check my window. Most of the time you don't need to go any different from 0 to 2 pi. That's what the 6.28 business is. The theta step, I didn't do that. It put it there automatically. X min and X max, now I did that, so I'll change those things. I don't think I'm going to need quite much. I only need, if the radius is 3, a circle of radius 3 like I'm expecting, then I only need to go like negative 4 to 4, and that'll be plenty of buffer to see the whole thing. So y min, I'll do negative 4, y max, I'll do 4, and then graph. And you can guess that this is going to look like an oval or an ellipse because the screen is not square. How do I fix it? Zoom 5. And it looks like a square. It looks like a circle now. Let's graph r equals 4 cosine of theta. And I think what I want to do is go through the effort of trying to explain how you get the answers you do. So what I'm going to do is draw. It's rough. I mean, we'll go and do it on the calculator when I'm done. But there was a time before calculators when we'd have to memorize different styles of these graphs. But I find it instructive every so often when you hit something that is new to you, and this isn't, but it may be a little rusty, to do things that you would do at the most basic levels and see what works and what doesn't. So let's go ahead and throw in different values for theta and see what we get for r. So when I start with theta equals 0, 4 times cosine of 0 is 4. And then I'm going to do a bunch of angles and then get the r values, and then I'm going to plot them. When r equals I'm just going to use the angles that we're supposed to know. So like when theta equals pi over 6, cosine of pi over 6 is radical 3 over 2. So this is 2 radical 3 for the r value. And then the next one we're supposed to know is pi over 4. Cosine of pi over 4 is radical 2 over 2, so this will be 2 radical 2. And pi over 3, cosine at pi over 3 is 1/2, so this will be 2. And then pi over 2 is where cosine is 0. Let's stop there and graph some of these. So if I start with theta equals 0, that means I'm on the x-axis. And then it says the radius is 4, though. So I have to go to where there's a 4 on the x-axis, and this is our start. Okay, now, as we proceed through our thetas, we start to move away from the x-axis, but counterclockwise. So the next angle that I have is at pi over 6. So if you can imagine an angle of pi over 6, it would be less than pi over 4, but it would stop. It wouldn't. 4 is bigger than 2 times the square root of 3. 4 equals 2 times the square root of 4. That's how you know it's a little bit bigger. So I'm not sure how much bigger, but I know what the graph's going to be when I'm done. So let me put this point here. And that was when it was pi over 6. I want to move the radius out of the way so that it doesn't affect my graph. Now let me move on. At pi over 4, that's halfway, we have 2 radical 2, a smaller number still. So at pi over 4, I don't want to touch the x-axis, but I wanted to see if I can make pi over 4 occur. So I think pi over 4 may be like that in length. That's just great. Now let's move on. Then pi over 3, so we're a little bit more like this, but the radius is only 2 this time. And then it's 0 at pi over 2. So when the radius would want to be straight up and down, when it would want to be straight up and down along the positive y-axis, the radius is 0. Now, I'm not You do the rest of these at all the angles that you know, fill in your R values, but here's what you're going to find out that you get. I know it's rough, but you actually get a circle whose center is at 2, 0. Not 2 theta, 2, 0. Now, what's interesting, though, is here is why those negative r's would be necessary. Let's take a look for an example when theta equals, let me see, pi over 4 to 3 pi over 4. When theta is 3 pi over 4, we're talking about here. When theta is 3 pi over 4, well, when it was pi over 4, we had this. So 3 pi over 4, you would expect a point here, but look what happens. When theta is 3 pi over 4, cosine of 3 pi over 4 is negative radical 2 over 2. This gives you negative 2 radical 2. Well, r would want to be pointing in the third quadrant if it weren't negative. Since it's negative, we reflect through the x-axis. And that is where the point is actually located. You see? The negatives were necessary for that to happen. Negative r values were necessary for that to happen. So you can see, as well, what ends up happening too is I only actually need to go all the way up to pi, because once you go r is equal to pi, you would actually get negative 4 for your r. So instead of plotting a point over here at negative 4, 0, reflect through the origin, and you come back to start again. So you only needed 0 to pi to graph this. You didn't need to do 0 to 2 pi. Get your calculator to do it. I say it so often, but I'll do it again. Calculator in radian modes, or you'll be sorry. Change the first thing to 4 cosine. Now watch the variable. When you press that, it becomes a theta now. And if I'm right, I think I've already got the window set at negative 4 to 4. So let's take a look. Since it was square, you can see that I had the z square set. You can see that we have a circle, like I said. And if you use a little bit of imagination, if this had been 4 sine of theta, I would have had a circle, but it would go along the y-axis. Now, there's more than just converting coordinates. I might say this, convert, let's see what example we were doing, example 9. Let's call this example 10. Let's convert that last problem, r equals 4 cosine of theta, to Cartesian. That means to change it to an x and a y. And the way you can do this is the following. It's weird. These are unnatural, what you try to do to make these happen. But x is equal to r cosine of theta, and y is equal to r sine of theta. And r squared equals x squared plus y squared. So this is, I'm going to be using these things. So the idea here is that you're going to try to force an r cosine of theta. I'll show you how you do it here. And r squared, if that happens, that's great. So let's go to r equals 4 cosine of theta. If I want an r cosine of theta to occur, I'm going to multiply both sides by r. I'll put it there so that we can see. But now, look at this. R squared is x squared plus y squared. On the right-hand side, we have 4x, because r cosine theta is x. And look, this is an equation in only x and y, and that's what we wanted to do. You could leave it here. I'm going to go a few more steps so that you can see why the graph is the way it is. So this is done. Let's make sure you know that. Check, finished. I'm going to go a little further. I am going to subtract 4x from both sides of the equation. I'm going to complete the square on the x's. That means adding half of the middle term, which is this 4, half of that is 2, but if I square it, I need to add 4. So what I want to do is rewrite this as x squared minus 4x plus 4 plus y squared. If I add 4 to one side, I've got to do it to the other. So I have x minus 2 squared plus, if you don't mind, I'm going to write the y squared as y minus 0 squared. And the 4, I'm going to write it as 2 squared. The reason why is it tells me that this is a circle of radius 2. Centered at 2, 0. Let's look at the last example and look at the picture that was drawn. The center is at 2, 0, and the radius is 2. Now, you, of course, won't have to memorize various graphs and things of that nature, but so all you've got to do to get a graph of the thing is simply clear your y that's already there and change it to the one that's given to you. So 2 minus 2 sine of theta. Let me do the graph and I'll adjust the window in a minute if I need to. Oh, how nice. This is like a heart. Actually, you know what it is? It's I think it's called it's like a lima bean, if you will. They got the weirdest name for this thing. You have I'll take a picture of it and put it on there. What you want to try to do is remind yourself how the graph is traced out. Starting at r at theta equals 0. When theta equals 0, sine is 0. So this is r equals 2. So when r equals 2, you're right there. And then you can sort of keep going. Like when pick a convenient angle to make sine work nicely for us, like pi over 6. Sine of pi over 6 is 1/2. Well, 2 minus 1 is equal to 1. So r is equal to 1 at the pi over 6. And then when you get to pi over 2, when the radius would want to point straight up and down, sine of pi over 2 is 1. 2 minus 2 equals 0. And you can see that you're at the origin again. And that the r's stay positive throughout the whole thing as it goes and does its stuff. This kind of a graph is referred to as a limosome. It's got the weirdest little thing underneath of it. You saw that, right? It's got like a little beard or something like that under there, but it's there. Other kinds of graphs. I'll just put pictures up, and you can use this as reference later. Something like this here. R equals 2 sine of 5. In this graph, they would call this a 5-leafed rose. So what happens is every 2 pi over 5, this thing comes back to 0 again. Well, you can see, actually pi over 5, every pi over 5 it does it, because if I put pi over 5 in for theta, sine of 5 pi over 5 is 0. So this thing also has a period of only 1, well, I wouldn't say 1 pi. It actually has a period of 2 pi over 5. Remember, you divide by that thing. But anyways, see if you can trace the way that r is drawn as theta increases. So you can see, like, when theta is 0, sine is 0, so you'll start at the origin, And then when theta goes and is like pi over 10, maybe that's halfway in here, you'll get a point there. And as it comes and gets closer to 2 pi over 5, it's coming back to the origin. Then after that, this is interesting. You should really watch the way this is graphed. Watch, it doesn't graph as you think it would. Let's go back to the window. Go back to the window, and I want to slow it down so you can see how it's done. I'm going to put 0.01. And I'm also going to, since I'm nowhere near -4 to 4 in any direction, I am going to, well, I guess because it squared it up, it's a little bit different. Let's do -3 to 3 and see if that's enough for the x's, and the y's, I'll do -3 to 3 also. And now let's watch the way it's graphed. It'll start at the origin, like I said, but watch. See, there it goes. It graphs the first leaf, but look what happens. It went into the third quadrant, and then it came back to the first quadrant. Do you see the way it's being drawn? And then finally, it gets to the last one. These leaves are 5 identical leaves because a period of only 2 pi over 5 gets the job, does a total cycle for each of these things. But you'll notice, though, that after pi over 5, like when I came in the first quadrant here, when I got to pi over 5, it was 0. But then what happens at more than pi over 5? Well, when you're at more than pi over 5, that means sine is dealing with an angle that is more than pi. Well, you have to be in the third quadrant for an angle like that. If you're just more than pi, you're in the third quadrant. So that's why it's doing this part next. And then coming through, it basically looks like it's going, and because pi over 5, when you multiply it by 5, is a whole pi quantity. Well, as sine flip-flops pi's, it jumps through the origin to, I don't know how you'd call it, an opposite quadrant, not an adjacent one. For something like this, you're left with the obvious thing, and that is to write r equals, so you could do your r1 equals the square root of 4 sine of theta, and then r2 would equal negative the square root of 4 sine of theta. And let's see what the graph looks like. I'll adjust as needed. I'm doing it slow so I can see what's going on here. Here we go. Ah, there we are. It kind of looks like a figure 8, doesn't it? So it did the top half, and then it went and did the bottom half. Do you understand why there's nothing in between here? Well, no, there actually is. I'm sorry, I spoke too soon. There is, but it's so shallow that it's hard to distinguish it. I don't know that this has a name other than a figure 8. So, anyways, there's one last well, let me put the picture of this down before I. So I suppose this is where your calculator will pay huge dividends, and you'll be glad you bought it, I guess. There is one degenerate case that I don't think I've mentioned. I know I haven't mentioned. But just like when you're dealing with a graph in x and y, sometimes we give you an equation like x equals 3 and it's a vertical line. Your calculator doesn't graph that. Well, there's a situation similar here, and it looks like this. Well, this is interesting then. If I make up a chart, I already have theta. If I call R1, 2, 3, 4, 5, theta is always pi over 3. Even for negative values of r. So what do you get? Well, since the calculator won't do this one, you will get a line through the origin of an angle of, I should have, I'll leave that theta there, but it's pi over 3. So this is like a degenerate case. This is like the vertical line in the Cartesian world. So bear that in mind. Your calculator won't be able to do something like that.